Good afternoon. My name is Joshua Vaughn, and I've had the great honor of being team lead of STARLabs over the past 5 months. I'd like to keep this brief because I know all of you have very busy schedules. That being said, on behalf of all of us here at STARLabs, I would like to thank you for reviewing and considering our current proposal for a new signal intelligence aircraft. I would like to start off by giving a brief overview of our company's goal throughout design. One of the most prevalent aircrafts in our reconnaissance fleet is the RC-135. This plane has been modified into a makeshift monstrosity in order to get as many components as possible onto one single airplane. Since our new plane will be designed from the ground up to be a signal intelligence aircraft, the RC-136 will be comfortably smaller and safely more efficient. Oh, and of course it'll be a little more faster. The RC-136 will have a cruise Mach of 0.78. Since our company is still in its infantile phase, I would like to take a moment to give a brief summary of how our company is structured. Despite having the workload separated into multiple different sub-teams, as you can see, we've had many members flex their skills and dip their toes in the different ponds. These members and their co-workers were the lifeblood of the RC-136.
Hello, my name is Kyle Spears, and I was the Aero team lead. After running an analysis on a variety of NACA airfoils along with the 707 airfoil as the baseline, the Aero team discovered the NACA 6409 airfoil to be the best fit for our design requirements. The requirements we were looking to fulfill included high lift, low drag, and a low moment to help our structures team. The wing planform was designed to be similar to previous signal intelligence aircraft, with a wingspan of 130 feet, a wing area of 2,650 feet squared, and an aspect ratio of 6.375. After using XFLR5 at our cruise altitude of 50,000 feet and a fixed angle of attack, we found our wing coefficient of lift to be 0.980 and a coefficient of drag to be 0.292. For high lift devices, our team decided to incorporate slats and double slotted flaps onto the wing of our aircraft. These are needed to achieve our CL max of 1.8. The conventional empennage configuration was chosen for our aircraft because of the wing configuration and engine placement. Sizing of the vertical and horizontal stabilizer was completed from using a stabilizer spreadsheet provided by a well-renowned professor at Oklahoma State University. The sizing and location from the wing were maximized from a stability standpoint.
So the first decision we had to make as a team was where we would like to place our engines and how many engines we would like to have, keeping in mind we would like to reduce the weight of the aircraft and be able to handle the N/2 engine out scenario from the RFP. We looked at fuselage mounted engines and wing mounted engines, also inboard versus outboard, and whether we would like 2 engines or to keep the 4 from the original RC-135 design. We ended up choosing 2 engines to reduce the weight and going with an engine that had a higher thrust rating and efficiency, and we would like to keep them mounted below the wings. Now that we know how many engines we need and where we would like to place them, we can pick an exact engine that fulfills our design requirements. We started looking at cargo engines and the CFM56 series, which they currently use on the RC-135. We looked up some thrust-specific fuel consumption data and kept in mind that the CFM LEAP engines that are now coming out promise a 15% increase in efficiency on the CFM56. We extrapolated that data and with the efficiency increase and found out that our worst case scenario thrust-specific fuel consumption will be about 0.51, and the LEAP 1A will give us a very high thrust rating of 32,900 pounds of thrust per engine, which gives us about 65,000 pounds of thrust for our 2 engines. Now that we have orientation, number of engines, and engine type selected, we can see how well that serves our design. As far as requirements that we've met or exceeded, our time to climb is 16.3 minutes, takeoff distance of 7,900 feet, landing distance 4,000 feet, which both do not exceed our maximum 9,000 foot requirement for the RFP. Our fuel weight is 138,000 pounds, maximum payload of 120,000 pounds, and a maximum range of 10,000 nautical miles.
For structures, we'll start out by talking about the different materials that we used or that we will use. We analyzed the most common materials in aircrafts, as well as different composite materials such as carbon fiber and Kevlar. We looked at two different types of aluminum, the 2024 aluminum and the 7075 aluminum. The 7075 aluminum has a much higher yield strength and ultimate strength with a slightly less Young's modulus. The 7075 is also a little bit cheaper. With that in mind, we decided to go with the 7075 T6 aluminum as the material of choice for the majority of the plane. We'll use that on things such as the skin and wing spars. With composites being high strength, low weight, and relatively low cost, we're going to use carbon fiber for the ribs of the fuselage and the ribs of the wings. This is going to give us a reduced overall weight of the aircraft and allow for more efficient flight. We plan on using both of these materials in unison to provide a strong, lightweight structure. For the load analysis of the aircraft, we have wing loading and fuselage loading. The wing load is about 340,000 pounds of loading due to lift. The wing load distribution follows a normal elliptical pattern with the max lift location at about 35% of the wing. We also have a maximum moment of 1,750,000 foot-pounds at the wing group. With the fuselage loading, the tail will be required to produce about 19,000 pounds of lift to counteract the moment. We have a static margin of about 0.2, which will give us a steady and level flight. For the landing gear, we're just going to use a traditional dual-wheel tricycle configuration, putting a gear on both wings as well as the nose.
So as far as the cockpit layout and the avionic systems on board our aircraft, we went with a glass cockpit configuration. This is similar to what can be seen in the A380 today. It's going to have 8 LCD screens, and on these screens it's going to show information from the engines, including temperature, RPMs. It's going to show weather. It's going to show everything that the pilots would need to really safely operate the aircraft. Backup instruments are going to be incorporated into this design in case there is a electrical blackout in the cockpit. It's going to be arranged in a common T configuration, which can be seen in the lower right hand corner of the screen. And then for the avionic systems on board our aircraft, it's going to consist of a whole lot of things, but key ones I'd like to hit on is the internal navigation system, automatic flight control system, flight management system. All these things work together to really make the aircraft operate as we would like it to. We went with the fly-by-light control system. This is preferred over a fly-by-wire due to the electromagnetic sensors that are going to be operating on board our aircraft. And compared to hydraulic and mechanical systems, it's a huge reduction in weight, which allows us to obviously carry more payload. So what this is going to do is going to take the pilot's input from the yoke, transmit it through fiber optic cables, and then once that signal hits the servos for the elevators, rudders, and ailerons and such, it'll move it with how the pilot wants to. The component layout, so our avionic systems is going to be held towards the front of the plane. Fuel is going to be mostly in our wings. We're going to have modular computers along the starboard side of the aircraft, and then there's going to be 20 payload operators sitting opposite those computers.
Despite the constant repairs and upgrades, the United States RC-135 airframes are showing their age. Spare parts are no longer manufactured, causing ground teams to improvise once the parts run out. The time has come for this aircraft to be replaced. Due to modern weaponry, communication, and radar technology, militaries must have the capabilities found in a signal intelligence aircraft. It is forecasted that Canada, the United Kingdom, France, and 17 other countries found below will be in need of SIGINT aircraft by 2022. Wartime scenarios are not the only way the RC-136 Star can be utilized. Due to its modular payload capabilities, the aircraft will excel in other applications such as maritime patrol, weather monitoring, and cargo transportation.